In this work, we introduce smoothness-aware path imitation learning on 2D images. We have released our code, model weights, and datasets on GitHub. Different from path planning on grid, we focus on 2D images. While typical path planning pursues the shortest path, a smoother and longer path can be safer by avoiding things such as building or traffic obstacles. Heuristic from empirical labeling given semantic labels or human labeling is more plausible. It considers both path shortening and smoothing. Therefore, a smoother path is often as important as a short path. Path planning methods often operate on maps with given obstacles and accessible regions, such as Dijkstra's algorithm, A*, and the any-angle θ*. However, they are either inefficient, limited in planning quality, or not necessarily lead to a smooth path. Learning-based methods usually rely on adaptive heuristic maps to avoid excessive node expansion. But they are not smoothness-specific or use expensive probability maps for learning. Hence, it is practical to consider both path length and smoothness and use more accessible labeling for supervision. Specifically, the path planning aims to find the optimal routine from a start node to a target node with the least cost. Each node is associated with a cost on itself or from its neighbors. Alternatively, the labeling can also be on edges. In A* algorithm, the distance heuristic can be from Chebyshev or Euclidean distance between a search node I and the target node T. We impose the angle between each two path segments in path-finding steps. However, directly minimizing the path angle could lead to a linear path from the start node to the target node. Hence, it is necessary to adjust the degree of the path smoothness using a min-max trade-off learning of the path angle. We name it path angular freedom. A small path angle often leads to a linear path as shown in DAA min. Otherwise, it has several zigzags to increase the angle. In contrast, a combination of both is more flexible to imitate given path patterns. We solve this planning problem using message passing. A message is passed from the start node to each of its neighbors k, then the one with the least cost is included in the path. Similarly, the node expansion starts from this selected node to its neighbors. Then it repeats till reaching the target node. We evaluate various datasets. References are computed from different path-finding strategies or human annotation. We evaluate the predicted path over its similarity with the reference path and its path length if the shortest path is requested. On binary maze datasets, our DAA* methods achieve the highest shortest path rate and path similarity among the learning-based methods. The learned cost map by our method shows the effective and fine accessible regions in the probability map. Our method also outperforms the state-of-the-art method transpath on the augmented TMPD dataset. This performance improvement also applies to the two video game datasets. Particularly, ours can learn a more sensible probability map for each semantic than neural A* and random walk. It aligns with the ground truth semantic map. It also achieves the best results on real-world drone view maps. We achieve a smoother path without crossing obstacles like buildings and roundabouts. The increased computation induced by computing the path angle is considerably low. For video game datasets, it is rather decreased due to the well-learned probability maps. Our method is end-to-end considering both path shortening and smoothing. We fully evaluate various datasets to highlight the importance of path smoothness in planning quality and safety.